When we gaze up at the stars on a clear night, we see countless points of shimmering light, each a sun, distant and mysterious. Among these stars, however, lie some of the universe's most extraordinary phenomena, red supergiants. These stars are not just bright, they are titanic in scale, with volumes so vast that if placed in our solar system, they would dwarf all the planets and swallow orbits whole. Red supergiants are cosmic powerhouses, giants that represent one of the final, most dramatic stages in the life of the universe's heaviest stars. Unlike the steady, medium-sized star we call the Sun, red supergiants burn their fuel at staggering rates, pushing the boundaries of what a star can be. These stars illuminate not only the night sky, but also our understanding of how matter cycles through the cosmos. Their vast surfaces and turbulent atmospheres challenge astronomers to develop new techniques to peer inside, to understand their explosive futures, and to reveal their role in shaping galaxies. The journey to becoming a red supergiant begins deep within enormous clouds of gas and dust scattered across the galaxy. Under the pull of gravity, these clouds collapse to form massive protostars, objects many times more massive than our Sun. These massive stars ignite hydrogen fusion in their cores almost immediately, and because of their great mass, the pressure and temperature inside them rise rapidly. This causes their nuclear furnaces to burn fiercely, emitting intense radiation and stellar winds that sculpt their surroundings. However, their extraordinary mass means that their lifespans are measured in mere millions of years, brief compared to the 10 billion-year lifespan of a star like our Sun. As the hydrogen in the core runs out, the core contracts and heats up, while the star's outer layers expand enormously. This phase marks the birth of the red supergiant, a star that can swell to a size hundreds or thousands of times the diameter of the Sun, with a surface so cool that it glows a deep red-orange. This transformation is not merely cosmetic. It signals profound changes in the star's interior and destiny. Red supergiants are among the largest stars known. Take Betelgeuse, for example, one of the most famous red supergiants in our night sky. It is estimated to be about 700 times the radius of the Sun. To visualize that, if Betelgeuse replaced our Sun, its surface would extend past the orbit of Jupiter, consuming Mercury, Venus, Earth, Mars, and the asteroid belt in a single, fiery embrace. Despite their enormous size, red supergiants have relatively cool surface temperatures, around 3,000 to 4,500 degrees Celsius, far cooler than the Sun's roughly 5,500 degrees. This cooler temperature is why they appear red or orange, a stark contrast to the Sun's yellow-white hue. But beneath this cool surface lies a violent and complex interior. The core of a red supergiant is a crucible of nuclear fusion, cycling through heavier and heavier elements. Helium fuses into carbon, carbon into oxygen, and so forth, creating layers much like an onion. The fusion processes generate incredible amounts of energy, which pushes outward, balancing against gravity, until the final stages, when the core can no longer sustain fusion. At the same time, their outer atmospheres are turbulent and unstable. Massive convection cells, some spanning a significant fraction of the star's surface, cause giant plumes of hot gas to rise and fall, creating dynamic brightness changes observable from Earth. These stars are often variable in brightness, their luminosity fluctuating as their outer layers pulse and shed mass. One of the defining features of red supergiants is their powerful stellar winds, streams of charged particles and gas blowing outward at tens to hundreds of kilometers per second. These winds carry away vast amounts of material from the star's outer layers, enriching the surrounding interstellar space with heavy elements like carbon, nitrogen, and oxygen. Over thousands of years, this mass loss can strip the star of a significant fraction of its mass, creating extensive circumstellar envelopes, clouds of gas and dust that absorb and re-emit the star's light in infrared wavelengths. This process is critical for the cosmic ecosystem. The matter lost by red supergiants becomes the raw material for future generations of stars, planets, and even life. Without this continuous recycling, the universe would be a far less fertile place. The study of these stellar winds is an active area of research, using sophisticated instruments to measure their speed, composition, and impact. Missions like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided detailed observations of these envelopes, revealing complex structures and unexpected clumps of material. The life of a red supergiant is a race against time. As fusion advances in the core, heavier and heavier elements are created until iron forms, a dead end for fusion because it consumes energy instead of producing it. When the core becomes predominantly iron, it can no longer support the enormous pressure required to counterbalance gravity. Within seconds, the core collapses catastrophically, compressing to incredible densities. This sudden collapse triggers a violent rebounding shockwave that tears through the star's outer layers, producing a supernova explosion, one of the most luminous events in the cosmos. The star can briefly outshine entire galaxies, shining with the light of billions of suns. The aftermath of the supernova leaves behind exotic remnants, either a neutron star, an ultra-dense ball of neutrons only a few kilometers wide, or if massive enough, a black hole, a region where gravity is so strong that not even light can escape. Supernovae also scatter the elements forged in the star's heart into space, seeding future generations of stars, planets, and life itself. This cosmic enrichment connects every atom in our bodies back to the fiery deaths of red supergiants and other massive stars. Astronomers have long been fascinated by red supergiants, and with advancing technology, we are now able to study them in unprecedented detail. The enigmatic dimming of Betelgeuse in late 2019 and early 2020 captured global attention. Observations suggested that a massive outflow of dust or a cooling of its surface was responsible for the sudden drop in brightness, a reminder of how dynamic and unpredictable these stars can be. Space-based telescopes like Hubble and the upcoming James Webb Space Telescope allow astronomers to peer beyond visible light into the infrared and ultraviolet, revealing the complex atmospheres and mass loss processes of red supergiants. Meanwhile, radio observatories like ALMA provide exquisite detail about the cool gas and dust clouds surrounding these stars, enabling scientists to map their three-dimensional structure and understand how mass loss shapes the star's environment. Such observations help improve models of stellar evolution, allowing researchers to predict when a red supergiant might explode and how that explosion will shape the surrounding galaxy. Red supergiants are key players in the evolution of galaxies. Their supernovae trigger shockwaves that can compress nearby gas clouds, stimulating bursts of star formation. They also regulate the chemical composition of the interstellar medium, injecting heavy elements essential for building rocky planets and organic molecules. Moreover, the remnants left behind, neutron stars and black holes, influence galactic dynamics, acting as gravitational anchors and, in some cases, powering phenomena like X-ray binaries and gamma-ray bursts. By studying red supergiants in our own Milky Way and distant galaxies, astronomers gain insight into how galaxies grow, evolve, and recycle their matter over cosmic timescales.